We have Ivonne Batan. Her study, a comparative study on carbon pools between restored and non-restored mangrove ecosystems in Miami-Dade County. Thanks, take it away.
Awesome. So, you guys are so nice. So again, my name is Ivonne. Thank you guys so much for being here. It's an honor to present this study here. So I am currently an interpretive program leader at Miami-Dade County Parks, specifically Deering Estate. But I also am, or was, a graduate student at the University of Miami's Erasmus. I just finished. Yay. Thank you, thank you. And this is basically my thesis, which is, again, a comparative study on carbon pools between restored and unrestored mangrove ecosystems in Miami-Dade County. Perfect. So a little bit of an introduction. I'm sure that we've all heard about mangroves. We live in Florida. We live in a subtropical ecosystem. We basically see them in our backyards every day. But they provide a bunch of critical ecological and societal benefits. They are very economically valuable, but also they provide ecosystem services for us, like cleaning our water, storing our carbon, etc. Right? They have the ability to sequester 4 times more carbon than terrestrial and other blue carbon ecosystems. And when we talk about blue carbon ecosystems, we specifically refer to biologically driven carbon fluxes and storage within marine ecosystems, not just mangroves, but also coral reefs, seagrasses, and other marine nearby ecosystems. So why exactly is this important? Well, for the past 60 years, we have reached atmospheric CO2 concentrations that have exponentially risen, and we are essentially reaching a global average of 422.7 ppm, according to NOAA, in 2024. I'm sure it's worse now. So there is a necessity for these ecosystems that are able to solve these problems naturally. So when we started this research, we broke it up into 3 main objectives. So first, we wanted to compare mangrove structure between restored and natural sites, specifically in our site, which is Deering Estate. We then wanted to quantify the above ground, below ground, and soil carbon pools of these sites. And then we wanted to take that and evaluate the ecosystem carbon storage and add an economic value to it. So it's not just for us scientists to understand, but it's also for other stakeholders as well to see a value, because sometimes it helps. So a little bit of background on this incredible site. So Deering Estate is a 460-acre natural preserve. It's nestled between urbanized areas, and it has 7 different ecosystems, some of them critically endangered, like pine rocklands. So out of these 460 acres, around 120 or so acres are mangrove areas. So it's a pretty extensive ecosystem. Particularly in this area here, that's one of our sites called Main Preserve. We have South Addition, which is located right over here, and then Chicken Key, which is an island about a mile out into the bay that you can kayak to. It's real nice. So a little bit actually about the history of this particular site. It is a cultural and biological field station. They have found Tequesta and indigenous remains in this area, so it is also an archaeological site. And it is actually a really cool area to explore how urbanized ecosystems are being pressured, especially now that we have things like water pollution and sea level rise, right? So this area here has been heavily disturbed, both naturally and through anthropogenic factors. So particularly in 1992, this entire area was razed by Hurricane Andrew. So all areas here were impacted. So these two, there's actually records of people who have worked at the park that right after that hurricane happened, all of the palm trees, all of the trees were essentially towards the front of the park. So the eye hit a couple of miles south of this area, so it was completely devastated. This area here, Chicken Key, is actually a man-made island. It's not a natural key. And it was made in the early 1900s when they dredged out the channels that are located in Biscayne Bay because it's so shallow. So they essentially stacked all of that sediment one on top of the other and formed what is now Chicken Key. So there's around 20 or so islands around Biscayne Bay that are very similar to this island right here. So now that we have that background, let's talk about how exactly we started this project. So essentially, we divided it into 2 parts, which was a structure and biomass, and then the actual soil carbon. So for structure and biomass, we went out into the field and we did transects throughout all our areas. So each of the places that we were doing our study, Main Preserve, South Addition, and then our restored site, which is Chicken Key, we did transects to up to 400 meters. So we fell in canals a lot, which happens. But essentially, we did the point center quarter method, which is PCQM. Those transects, we stopped every 10 meters or so. We took data points like diameter of breast height, regular height of trees, and the distance between the trees to find out these particular data points. So after that, we took that data, we put it into the mangrove structure R package, and that was created by Araujo, which is one of my advisors, and Shielder, and that gave us some of the structural parameters of the forest that tells us how exactly that forest looks or is growing. After that, we used allometric equations for the above ground biomass and then below ground biomass to see the production of that. So now soil carbon, which is a whole nother monster in itself. So for that, we used a Russian P-bore, which is this beautiful instrument here that looks and is very heavy. So we had to drag that through the transects all over the mangroves, which, as you can imagine, is very wonderful. But essentially, that allowed us to get cores, so we could see the actual percentage of carbon that's inside of the soils within this ecosystem. So apart from that, we also use what is called the highly aggregated sampling technique. So essentially, we would have a core like this. Every 15 centimeters, we would take that sample, we would put it in a tin, and we do that because carbon changes with depth very slowly. So maybe the first 15 centimeters is completely different from the next 15 centimeters. So that allowed us to visualize that soil and also get a soil profile as well. So most of our cores were with depths of 50 centimeters to 1 meter. Since we were so close to the Miami Rock Ridge, sometimes it was incredibly difficult to get an actual core past a certain depth. But some areas, they were a lot more agreeable to work with, so we were able to get full standard 1 meter. Finally, those soil samples, they were taken to the Cirque Blue Carbon Analysis Laboratory at FIU. And once we got those results back, we also used a formula that we adapted from Jaroth et al., and we added that valuation to it. So now for results. So essentially, what our data points told us was a story. And the story was that this particular ecosystem was disturbed. And what we saw was a regrowth pattern that was happening by both sides. So originally, when we were doing this, we thought, okay, we have a restored ecosystem and we have a natural ecosystem. We think that the natural ecosystem is obviously going to have a lot more carbon, it's going to be a lot more structurally sound, etc. But what we found is that the growth trajectory for all sites, they were very similar because they were heavily disturbed. So for example, we have mean DBHs that are very similar for all three sites. Natural sites had a little bit more of structural complexity, but they were more or less similar. But you did see a lot of height, which means that these trees are trying to restore that canopy by growing higher. Apart from that, we also saw tree density. So tree density was high, which is very agreeable with the fact that these trees are trying to grow back, so they're all very close to each other. Mature forests are going to have larger trees that are not so close together. And finally, you can also see here in above ground and below ground biomass, there's a lot of above ground biomass, which means that that canopy is trying to regrow that vegetation at the top. So now for probably the most significant part, which is the actual soil carbon. So although there were structural differences in above ground and below ground for both sites, we found that the soil carbon itself was comparable between the two, which means, and it reinforces that the soil carbon pool is the most, how do I say this, the most stable of all of the pools, right? Which is very significant. So let's say that there is a disturbance. That disturbance is going to pretty much take away all of the biomass that's here. But this here, although it was heavily disturbed, it's still comparable, which means that that pool is the most stable pool. So afterwards, we added that valuation formula. And essentially what we found was that although this is a very small urban preserve, we were able to get a good, pretty much evaluation of what that area is, right? So it's just over 1 million, which is pretty cool. So we divided this into high-end value and low-end value. We wanted to provide a conservative estimate, right, which is what you see here. Of course, this valuation, this reflects existing carbon stocks and excludes future sequestration and potential long-term carbon credit generation. So this is not the final number. This will probably grow as the ecosystem starts to grow and develop more. So what are some key findings? So first and foremost, natural mangroves, they store greater total ecosystem carbon than restored carbon. Of course, these islands, one is natural and one is man-made, so they do have different growth trajectories. However, soil carbon remained the dominant carbon pool across all sites, which provides us the insight that that carbon pool is stable. So some significances and why this is important in the first place. Well, this is the first structural and blue carbon assessment done at Deering Estate. We don't have any data previously, at least in the structure of the mangrove, so this is a baseline study. So once again, we found that that soil carbon remains a dominant and persistent carbon pool even after disturbances, which is what we saw in 1992 with Hurricane Andrew that pretty much devastated the entire area. Restored mangroves, they can recover substantial ecological and blue carbon function over time, which means that mangroves are worth restoring, especially in urbanized areas like these. And disturbance and restoration shape long-term structure and carbon storage, as we saw with the data from Chicken Key. Finally, results can inform future restoration, conservation, and coastal management practices. This is important because now we know that their blue carbon pools, they are basically the most stable. So essentially restoring these ecosystems is worth doing, right? They're gonna store that carbon. That carbon's not gonna be out into the atmosphere. And you're basically going to be contributing to easing what we have known as climate change. And this supports identification of coastal carbon sinks across Biscayne Bay and Miami-Dade County. So although this is a master's thesis, we do want to continue this work. The idea is that we can do this, but with mangrove green spaces across the county. So we essentially form almost like a network of green spaces that we can pretty much add a valuation to it, but also see how much carbon those places are storing. So some conceptual takeaways. Natural mangroves, of course, they maintain greater structural complexity and ecosystem carbon storage than restored systems. Restored mangroves can still recover substantial blue carbon capacity following disturbance, as you saw in those graphs. Although the above ground and below ground biomass were different, the blue carbon pools remained pretty much competitive, essentially. And that's because they can still recover that substantial carbon soil amount. And of course, one of the most important things is that even fragmented urban mangroves like Deering Estate, they may collectively function as sort of like a network of blue carbon green spaces across heavily urbanized areas, especially here in Miami-Dade County, which is, in my opinion, extremely important. Thank you.